series connection. Now in the parallel connection, what I really tell you here is that there's no way you can do the matching if the real part of your normalized admittance is equal to 1. So you see, just from your basic circuit and then the analysis, you can see there are two ways you can do the matching using inductor and capacitor to cancel out the imaginary part, such that your total impedance, your total admittance becomes a real number. And that real number, if you are doing the series connection, you are going to have no reflection only if the real part of your impedance equal to 1, normalized impedance equal to 1. If you are doing a parallel connection, you can only achieve gamma equal to 0 only when the real part of the admittance equal to 1. Yes.
You know why
Huh?
you know why
When I think about the admittance, I normalize with respect to 1 over z, 1 over z0. Okay, in other words, I normalize to y0. Okay, so you see that the point here. When you are talking about the admittance, you normalize to the admittance of your transmission line. When you are talking about impedance, you normalize with respect to the impedance of a transmission line. Okay? It makes sense. You see, the normalized, when you talk about normalized, it's a dimensionless number. Okay? So, follow me there. Okay? So, there are these two ways. If you are living in an ivory tower, you can do either way of that. And I bet 99% of you will prefer to do the series connection. Easy. Okay? I was a student once, even though I was ancient time. But summation is always easier than doing the division. So you prefer the series connection. However, practically, this is a more practical way of doing this. So that's the reason we teach you more emphasis on the second case. Okay? So let me repeat one more time. Theoretically, you can do either way. Okay? Theoretically, you can do either way. But the thing here is that the transmission line is already there. The antenna is already built. So what are you going to do? You are going to cut over the transmission line here and then insert your circuit component there. It's a little difficult. Okay? But you can actually solder another component on top of that. So that's the reason you make it more practical to do the parallel connection. So that's the reason if you see the transmission line kind of textbook, we more or less almost focus, emphasize on the second situation. Okay? And that's the reason when we talk about matching, we use the Smith chart as an admittance chart. Okay? So here, another thing to tell you here is that how you use the Smith chart as a admittance chart. You first using it as an impedance and rotate 180 degrees, then you are able to find the admittance. That's a trick to do that. Okay? So now, think about this is that how can you do matching? When we say matching, that means gamma equal to 0. Gamma equal to 0, you need to have two conditions. One is the total admittance at a location must be a real number. And the real part of that admittance must be equal to 1. So you can cancel out. So you need to have these two conditions match. One is that at that location, the total admittance must be a pure real number. But pure real number is not enough. It has to be equal to 1. Okay? But I'm talking about the total admittance. But the true admittance will have an imaginary part. That's where you add the circuit component to cancel. It doesn't matter how big or how small that that the imaginary part, you can always provide a capacitor or inductor to cancel it out. Yes?
So the first condition is met by changing the value of your circuit component, your capacitance or inductance.
To cancel.
Then the second condition is if your V0 doesn't happen to be your RL, you have to you're moving your component along the line to the right wavelength.
So to the right location when your real part of your admittance equal to 1. So you see, that's what I was joking to you guys about it, is that when you cannot solve the problem, you change the problem. So I want you to match this transmission line, and if you want to match it right at the location of your load, you cannot do it. You change your problem. Find where you can do the problem. In other words, you move around your transmission line to find the location where the real part of your admittance is equal to 1. And that will be the location that you're going to add the circuit component. So you see, very good. So you actually follow me good.
So the way that we're doing the Smith chart, like we find out the matching capacitance or inductance load, and then based on that, we find where that lines up on the Smith chart, and that's how we find where that nuisance is 1.
Oh, no. You see, you have this load impedance already. So you have a load. So you can draw a point on the Smith chart. And if you want, you can rotate it 180 degrees to find the admittance on the Smith chart. And then along the transmission line, one thing don't change along the transmission line. The magnitude of a gamma don't change. So you take this point and connect it to the center of origin. You are able to draw a circle here. Center at the origin, and here is the one point on the circle. So you draw a circle. Constant radius circle. On the Smith chart, we also see there's a lot of circle, and then there's a circle on the top and on the bottom. So you want to have the admittance, the real part equal to 1. What does that mean? This constant radius circle need to intersect R equal to 1 circle. And that is the location that I want to match. So you go from there to find out, how much workers I need to rotate on the transmission line to get to this point. So when you get to that point will have a value of YL equal to 1 plus something, 1 plus JX. Now you provide that minus JX to cancel it out. And you move from this point to the center. Okay? So let me use an example to show. So that's the sort of math behind what we are doing. So now let's look at an example that we're doing.
Again, back to your
Yes?
yeah,
Go ahead.
so back to your first point. So with this chart here, you're saying this is impedance, now it's a distance. You just do this, right?
You can do that, but I prefer just kind of rotating 180 degrees, okay? Not rotating your chart, but rotating your point. Okay, I prefer that way. Yes, you got it, okay? So, let me, just you may want to become a best friend with a smith chart. With a smith chart with you, at least in the next few lectures. So the first thing you do is actually for a problem which we are going to show, you first identify the impedance, and then after that you normalize that impedance with respect to Z0. So you got a real part, you got an imaginary part. So you go to the Smith chart. You see all those circles that you hear. You see here, this is a big circle corresponding to R equal to 0. And here's R equal to this and this. And also this is a circle which is passing through the origin, which is R equal to 1 circle. Okay? So you look at all the circle and find out which circle corresponding to the real part of your impedance.
Your
Normalized impedance. And then you go and look at your imaginary part. If that imaginary part is positive, it's on the upper. If that normalized impedance, the imaginary part is negative, it's on the bottom, that's capacity. So you find that small circle, and then the two circles will have an intersect, and that is the location of your impedance. And you draw that impedance point, and then connect that impedance point with the origin. Go to the other side, 180 degrees, the same distance.
So
Then you find that
so if it's 3 inches, and you just measure 3 more inches.
Yeah, again, use the compass. You can use it to do that. Constant radius circle. So you go from this point on the circle to the opposite point on the circle. Okay? And then to answer your question, then you have this constant radius circle now. And that constant radius circle is going to intersect with R equal to 1 circle. And that's the point. The intersect is the point that you want to do the benching. Because that point will have the admittance equal to 1, the real part of admittance equal to 1.
And there's going to be 2 points, right? And you want the one that's the opposite sign. Like it's matching, so if it's the positive, matching.
Your major, yes. Your major, yes. What's your major? ECE, right? We are engineer. You know what engineers do? We are cheap. So there are 2 solutions. You choose the one which is cheaper. You can understand what I mean by cheaper?
But they both work.
They both work.
Okay.
Okay. So you want to choose the one which is cheaper. You are going to see the location you choose will also affect how much wire that you need to provide in order to match it. And you want to choose the one which is cost you less. Okay. Theoretically, you can have an infinite number. Okay. But also the transmission that may actually only have a finite length. So that's another consideration. Yes.
You know the length along the line where you have to place this new component based on the wavelength at that point?
Exactly. Based upon the wavelength, the difference between your wavelength, the difference between your endpoint and your starting point. That's how much you need to travel. Okay? Not based upon the final destination. It's based upon your final destination compared to where you start. That's how much you need to locate.
Where you start being like the generator side?
No, it's on the look. You see, you start by plotting on the screenshot your normalized impedance. And your normalized impedance is at the look. And you move toward the generator. So when we say the intersect, like he said, there are 2 points. So you need to take your original admittance point, and you need to move clockwise toward the generator. Toward the generator. You are moving toward the generator. See what I'm saying?
You're moving along a circle you draw centered at the origin?
Yep.
Okay.
Yeah. Okay. So let's use this example to demonstrate. Okay. So I kind of give you some preamble now. Let's see how we do mechanically, so you can understand exactly what I was talking about. So let's look at this example. This example, we have the load, which is a 25 minus J50, and your transmission line is a 50 ohm. So your transmission line is a 50 ohm. So this is the first step. Step number one, from that load impedance, I compute the normalized impedance. And normalized impedance is simple, just taking that and divide it by 50. Once we do that, we find out our normalized impedance to be 0.5 minus J1. Okay? So you go on to your Smith chart to locate that point. You see, the point is real part is equal to 0.5, isn't it? Right? The real part is equal to 0.5. Look at this point, which I drew here. This is on the 0.5 circle. Okay? So that's a 0.5 circle that you see there. And then the imaginary part is equal to what? Okay? So that's how we find this point. This point is the intersect of the XL equal to minus 1. And RL equal to 0.5. So this is the intersect of these two circles. So you get this point. That's your normalized impedance. Follow me? How to identify the point on the Smith chart. The real part is equal to 0.5. The imaginary part is equal to minus 1. So you find this point. Once you find that point, take out your compass. Make the center to be origin and the constant radius passing through that circle, passing through that point, CL. And that is that constant circle which I drew. Look at that constant circle. So in that circle, every single point is equal distance to origin. In other words, your reflection coefficient, the magnitude is the same. Okay? And the second step, which I do, I take that impedance, rotate 180 degrees, go to the other side. That will be my normalized admittance. Okay? That will be my normalized admittance. Now, where do I want to go in order to do my matching? I'm taking that constant circle and intersect with R equal to 1 circle. And that's where I get that point, which I label to be the Y on that location. So you see, step number one, identify the point. Identify the point of your normalized impedance on your Smith chart. And take out your compass and draw this constant radius circle. And then rotate 180 degrees to the other side. You find your normalized admittance. And then this constant circle and this R equal to 1 circle is going to have an intersect. This point and this point. Okay? This point and this point. So if you choose this point, then you will need to rotate from this location, rotate onto here. You will take a longer distance to travel around the transmission line to get to the other side. So we choose the point because it's closer to your load. Okay? If you do and choose on the other point, it's perfectly fine with me too. They are correct solutions. Okay? We choose the one on the top because it's closer to the load. So it means that now the distance that you need to travel, so how do we determine how much wavelength you need to do? So you see, you take this point here, then you read from your Smith chart what is the wavelength. So the wavelength here is about 0.178. And you look at from your Smith chart, this point, the radial line intersect on the circle here is about 0.115. So you have originally you are at 0.115 lambda, and you get to the end, which is 0.115 0.178. So you take a 0.178 minus 0.115. Then that's how much wavelength you need to go to find a matching location. So let's go back to the, see here, one, you find out the normalized impedance, and you rotate the 180 degree on your Smith chart to find out the normalized admittance. And rotate it toward the generator to the matching point where the real part is equal to 1. That's where we say the intersect of these two circles. And that tell you at a location what is your real part must be equal to 1. What is your imaginary part? You look at that point intersect with the XL location. And this time is 1.5. So that means that you need to provide a matching of a minus J1.5 can cancel it out. Okay? So you need to provide, but here is the distance. Answer your question of how far you can travel. You read from your Smith chart the radial line, and that's 0.17 lambda, 178 lambda, minus the original one is 0.116 lambda, which tells you need to rotate toward the generator. You need to move toward the generator by 0.062 lambda. Okay? Now, this is your matching. So this is your matching. You need to provide a minus 1.5 kind of admittance in order to cancel it out. Okay? So you need to provide this 1.5 admittance to cancel it out. And that's then here's the question: is how to provide a parallel connection which provides you the J equal to the minus J1.5. Okay? Admittance is equal to minus J1.5. What is that? Capacitor or inductor? Huh? Say again?
When you take one over it, the J would be positive, so
Yes, you need to provide inductor. Okay, you need to provide inductor. So in a straightforward way, you will say, why don't I just simply go to Radio Shack and buy an inductor at a frequency such as omega L is equal to the 1 over omega L is equal to 1.5. So you can find out what inductor that you need and then connect to that. Okay? Microwave, we don't like the lump circuit. So we want to fade using transmission line itself. Okay? So we will, and this will also provide a wider band kind of matching. So here is what we do. We use you can use a short circuit or open circuit transmission line and adjusting the length, and you will become an inductor or become a capacitor at the location. In this particular example, we are using the short circuit. We are using the short kind of transmission line to kind of behave like the inductor at the location. So depending on the length that you have, it's going to be either inductor or capacitor, depending on the length of the transmission line. So what am I talking about? Again, let's go out to the transmission line. So now, at this moment, I want you to completely switch off. Okay? We already done the Smith chart, so we find the matching location. The real part is equal to 1. The imaginary part is 1.5. So the problem becomes another problem. How do I find an admittance which has a minus J1.5? Okay? To connect to it. So you already done 50% of your problem. The other 50% is how to make an admittance which is a minus J1.5 to connect to it. Okay? So this is second problem. So now the first problem is done. So let's go on to the second problem. The second problem that we do is we are going to use a short circuit transmission line and adjusting the length in such a way that at this location, it actually have an admittance of minus J1.5. Okay, so on here, short circuit. Short circuit, you know very well, short circuit, the Z must be equal to short circuit. If it's short circuit, what is your impedance? 0, right? So impedance is equal to 0. That will be this point here. Two ways to look at it. One, that's the intercept of R equal to 0 and X equal to 0. Two, when the ZL equal to 0, what is your reflection coefficient? Remember, gamma is equal to ZL minus C0 divided by ZL plus C0. So if ZL is equal to 0, what do you get? Minus 1. That's the reason it's on the left. On the right, that's 1. On the left is minus 1. So that is impedance. How do I get the admittance? Rotate 180 degrees. So that is admittance location. So your impedance is equal to 0, your admittance will be infinity. So you take this impedance here, rotate 180 degrees there. So that transmission line, the reflection coefficient of magnitude is always equal to 1. Again, the constant circle. Again, the constant circle. So short circuit, impedance will be this point, admittance will be this. So this is the corresponding to the major circuit, the admittance will be equal to infinity. And if you adjust that transmission line length, it will be on this circle here. So this big circle intersect with X equal to minus 1.5 will be the location you are looking for. So this corresponding to X equal to minus 1.5. So you need to go from the short circuit to here. And this is the distance that you need to travel. And here is, if you look at here, it will be, say, 0 wavelengths, and then you go from this point to this point. It tells you how long that transmission line needs to be in order for a short circuit to become an inductor with the admittance of a minus J1.5. So let me repeat one more time. This is where the transmission line is kind of like a magic in a way. You can take a short circuit, a wire which is short circuit, and adjusting the length of your transmission line, it will become an inductor. You go from that short circuit and you travel down here. Every single point down here is an inductor. Okay? Because this is admittance now we're talking about. So you see, you can take a short circuit and become an inductor. If you make it long enough, you will become a capacitor. So a short circuit can behave like an inductor, can behave like a capacitor, depending on the length of your transmission line. So now in order for you to get that admittance to be minus 1.5, you go from that point, rotate to here. So you read from your Smith chart here, this is about 0.3 something, and that's 0.25. So it can tell you, so if we go back to my, here it tells you that is the 0.344, that's the final destination, and your short circuit location is corresponding to 0.25 lambda. So the distance that you need to travel is 0.094 lambda. So that means that that show the matching transmission line need to be 0.094 lambda long. If that's a 0.094 lambda long, then the admittance will be minus J1.5. Adding together, the total will be your load impedance plus your matching impedance, your load admittance plus your matching admittance, and the imaginary part will cancel each other out. So the total admittance now will become 1. On Smith chart, it moved from the point to the center.
Where'd you get from 0.25 from? Line 5?
Look at your Smith chart. That's the difference. Look at your Smith chart. Here it tells you it's 0.25. Look at this number here.
Okay.
0.25.
Oh, okay, so it goes from here to
Yep.
the outside.
So you actually intersect your Smith chart on the outside, and then number tell you what's the reference. Okay? And you intersect that, the other side will tell you it's a 0.344.
Okay.
That's where I got the number. Yes.
So you don't actually have to place an inductor or capacitor into these circuits, you can just use a transmission line of different lengths and it'll have it.
That's a transmission rate, it's one way. Okay. And doing this is better this way. You're doing this, you actually have a wider matching. So when you are at a different frequency, then you're going to have a gamma not equal to delta that is small. So you have a better benefit. If you put into the left circuit of that L right there, what is that that L may behave differently. When you connect to it, it will have the capacity effect there already. 2, it actually is only like inductance at a particular frequency. So if you go to a different frequency, you still use the same inductance, your gamma actually will be bigger than using transmission line. So this is actually a better technique to get the wide band operation.
So, physical sense, you're just attaching another wire.
Say again?
In a physical sense, you're just attaching another wire.
Exactly. You see, think about it. What is an inductor? Have you ever looked at an inductor? It's really just wire. Okay?
Yep.
Right? So this is to some degree, it's really not a magic. Okay? It's just you take your wire in a different way. Again, this is you can think about this is the coaxial cable. And I have this coaxial cable and then adjusting the coaxial cable to be 0.062 lambda long, and then I showed my coaxial cable in here, and that becomes a inductor. At a frequency. Okay? The inductor you keep on talking about is at DC. So that's kind of makes sense to do this kind of a thing. But now, you are talking about inductor at 1 gigahertz, then that's slightly different. This kind of wire at 1 gigahertz may not be the same 10 to the minus 8 Henry as you expect. That's one thing. Second thing is that even if it really is a 10 to the minus 8 Henry at 1 gigahertz, at 1.1 gigahertz it can be different. But using this as transmission line, if the coaxial cable is a high quality coaxial cable, it's always a TM wave. So the impedance will be 50 ohm and the speed of light is still fairly constant. So it's much controllable, much more controllable. Any other question? That's a good question. Yes?
So when you determine where the cable put the wire, do you actually cut the wire there, or do you just you make the line shorter?
You solder on another solder. It's in parallel, not in series.
Any other question? Yeah. Okay, so here is how you use a Smith chart. We're going to go through how to use a Smith chart one more time on Wednesday using some other example. But now you start to see the math behind it and how we do mechanical. Okay? Question? Before we go? Then I will see you Wednesday.